So we have next, on Wednesday, on Wednesday we have the last day before spring break. I don't know if, I mean, I'm perfectly happy giving you guys a quiz. You guys will probably say, we don't want a quiz over this homework, but the thing is, if you don't have enough quiz grades at the end of the semester, you have a lack of quiz grades. So if you did poorly on one quiz, then it doesn't show up as anything. So I prefer to have a quiz, but I'm going to leave that up to you if you want to have one before or not. It'll be over the homework you just did and are turning in. No quiz? No. All right. All right. So then turn in the in-class assignment / homework.
Which one, the Kaylee paper?
Everything that I assigned from the homework and the in-class assignments.
We're only 4 problems, right?
I think so, yeah. That's about what I did. 4 long problems.
Do you want the one from last week with all the rotations and reflection?
No, because I have I walked around to make sure people were getting it right, so I think that was pretty self-explanatory.
Okay, cool. Yeah, good. Thank you.
Huh? No, I know like Brian's input. She's telling me on the other day, she said it's like that. That's why it's like
Okay, so to give you an update on where we are in schedule, we've actually been hit hard because of all the snow stuff going on, but where we are on schedule is that when we come back, we'll have a quiz over the homework that I'm assigning this week, which I think I can get through a lot of it today, some of it on Wednesday. Exam 2 over everything is on March 25th. And remember, the exams are comprehensive. I mean, you're learning more and more as you go. It's all like all these examples kind of come together, and I see you guys actually drawing those examples out when you need to and thinking about things. And again, lots of good questions coming my way. So where are we in the book? We just finished up the section on permutations, and now we're looking at direct products of groups. I wanted to skip this chapter and go forward, but then I realized that there's a lot of interesting examples that you can come up with from direct product of groups. You can kind of see, I think, from what you're doing and the problems that you're looking at that I'm assigning you now, that a lot of the thinking involves coming up with the right example and thinking about that one example, because you want to write whether something's true or not. If you can think of the right example that makes it work, it'll tell you the why. And when you can think of the counterexample, it can tell you why not. So I think that I didn't want to skip this because a lot of the nice examples come from direct products. So that's my reasoning, that important examples can be generated using products. So I want to define what a direct product is today and how direct products can be used to construct larger groups from smaller ones. A lot of times they are used, at least the way I've seen them, used for a counterexample to something that you think might be true always. Number 2, there's 2 kinds of products. There's something called an external direct product of 2 groups, and how this operation is defined. And the external direct product might be something you've seen before. How do you find the order of an element in a direct product of groups? So you know what you're doing is you're taking small groups and patching them together. So using that knowledge, can you find the order of an element in the larger group? And the 4th thing is, what is an internal direct product of groups, which you might not have seen before, and what conditions are needed to define that. And they're linked. They're linked, and there's similarities and differences between those 2 things. I had the wild idea that we'd get to homomorphism, so you have a nice kernel to the image space through a homomorphism up there. Nice diagram. But the intuition is, if I'm working with Z, I can think of combining integers by adding or multiplying. So in fact, the first groups that you looked at, you were looking at ways to pair objects together. So I showed you the example of braid groups and how we compare the two braids together, just to give you an example of something where you're just pairing things. What now we'd like to do is to pair entire groups together. So if I have 2 groups, G1 and G2, I could put those 2 groups together in a similar way. And we can do this by forming what's called the Cartesian product of two groups. The Cartesian product you see in real analysis class, you see it in linear algebra. You can actually take the Cartesian products of Z2 over and over. And that actually is a vector space over a finite field. So it's a different kind of field. So it's kind of neat. Then the external direct product, what we mean by that, so the notation changes from, some people just use the x only to define the Cartesian product. When we put that direct plus with a circle around it, what we mean is the external direct product. It's the set formed by, the group is the G1 cross G2, equipped with the binary operation where you just pair it the way you think you should pair it. R1 star R2 would be the direct, you know, this would be the binary operation from G1, and this would be the binary operation from G2. And I believe in Fraley he might have put a star with a little G1 underneath here and a star with a little G2, but I thought it was a lot of notation in there. So for example, Z2 cross Z2. By the way, Z2 is my favorite field. I can't make a sign error in it. And Z2 to the n is my favorite vector space. And you can define some really hard problems on Z2 to the n. These really nice problems. I can give you guys an open one in a couple days. Maybe on Wednesday I'll show you an open problem on Z2 to the n. I think that has to do with Descartes, but yeah, the Cartesian plane, really what you're doing is crossing R and R, so I'm not sure the history, but Fraley has history in his book, so it's one of the nice aspects. And in PDEs, well, we only had 4 people in there, so we could, do we have 4 or 3? We had 4. So we actually started every lecture with a history of one mathematician whose name kept showing up. And it was kind of cool, like, there were so many similarities of their lives that you kind of think, I had mentioned to Jeff, saying you're a mathematician, that's part of your soul. Everybody kind of has the same feeling as they go through it. So when you take Z2 cross Z2, you can write down the Cayley table, and it's not as difficult as writing down the Cayley table for the quaternions. You can definitely just see that the identity is going to come down the center because you can you're adding, right? The binary operation, each one of the Z2s is addition. And these would be the other pieces. So for example, if you take 1, 0 and add it to 1, 0, you get 1, 1. Or 0, 1, sorry. This is what you think it should be. And if I'm correct, Hungerford, I think, does a lot of Cartesian products, right? Because the idea in Hungerford is that they're more infatuated with the vector space structure and the ring structure. And that's where they start. There's a really, really fantastic book. And yeah, I bought the book to actually do some really neat mathematics, and then I started drifting off into applied mathematics. But it's called I think it's called Linear Algebra over Commutative Matrices. I want to say it's just the ring structure. So you don't have a field, but it's over rings. Commutative matrices over rings, something like that. But it has a lot of these ideas where you will get where Hungerford is coming from. I would think he'd be a fan of that book. I'm going to bring it in here because it's a really neat book. Okay, so the obvious theorem that comes from this is that the direct product of G1 circle plus G2 is a group. And that's actually fairly easy to see. So if I have that, so I chose 2 groups there that I crossed that have the same orders, but if I have 2 different orders, can you predict for me what the order of the direct product is going to be? And maybe you want to start with problem 2 first and find the order. What about the order of the elements? So you know something about the order of each element separately in its little piece group, right? G1 and G2. Can you tell me something about the order of that element in the new group? So here's some free play exercises to get started and get warmed up. These are fun. Much more fun than doing the quaternions, the Cayley table for the quaternions.